Okay, two last very quick notes about diffraction before we move on to Doppler effect. You can see diffraction lots of different places where there's bodies of water. Matter of fact, the town park, there's the fountain in that little circular part of the pond, and then there's an opening in that little retaining wall that goes out into the bigger pond. If you look on a very calm day when that fountain is on, you can see the ripples moving outward. You can actually see diffraction in that pond. If you just go on like Google Maps and you look at coastlines, it doesn't take very long to actually find a picture of diffraction. We have one right here. We have a coastline. We have two little small islands here. They are actually acting as our barrier. You can tell if you look closely that there's some wave fronts, and I'm being very generous with my wave fronts here, kind of in this general direction. I didn't label all of them, but then after the waves move past these little barrier islands, they start to make this sort of pattern. Okay, that is diffraction happening in the real world. Okay, waves spreading into the area behind some sort of barrier. This last thing, I wish I didn't have to teach about, because if I didn't, if this wasn't asked about, I would have had a student my first year get a 100 on the Regents. There was a question on the Regents. I will point out exactly what question it is to those of you who take that practice Regents, that asks when diffraction would be the biggest, and I gave a couple of examples. Okay? The amount of diffraction, the amount of this bending of waves is greatest if the opening in the barrier is small, and if the opening is about the same size as the wavelength of the waves going past it. Okay? I had a student who had everything else right. He had a question like this. This was my first year teaching. I did not talk about this because I did not think that this would be a question on the Regents. And then he basically got it down to the two choices that seemed more correct, and he picked the one that was unfortunately wrong. So I always say, if I spent 30 seconds talking about this that first year, that student would have had a 100. Oh well. So, we talked about Doppler. Okay, so that's it on diffraction. We've got to go to Doppler effect now, and you've all heard of probably Doppler radar. We'll talk about what that is in a little bit. You all actually know what the Doppler effect is. 4-year-olds know what the Doppler effect is, okay? But maybe you've never heard the principles stated. But you all kind of inherently, just from your life experience, know what it is and know what it means, okay? Let me play you a little video real quick. The video quality on this is terrible, but this will illustrate my point if you listen to it. Okay? Here's an ambulance that is coming, or a fire engine that's coming at you right now, and then, after about halfway through the video, it switches to moving away from you. I want you to notice what is different, other than just the loudness of the sound. Here it comes. So, something kind of interesting happened there. And it wasn't just it got louder and it got quieter. There was a distinct difference in the pitch, okay, or in the tone, or in the frequency, we might say. It was high-pitched when it was coming towards you, and then you could hear that the pitch got lower, okay? This is the same thing that little kids do when they're playing with cars, okay? Little kids playing with cars, and they know from experience, from riding around in mom and dad's car, that when something's coming towards you, it has a higher pitch. When something's coming towards you, going away from you, it has a lower pitch. That's why little kids, when we try and imitate cars, go, meow. They're lowering the pitch. You guys can all make fun of me for doing that now. So you know already from life experience that when an ambulance or police car is moving towards you, its siren sounds really, really high-pitched. And when it begins to move away from you, the pitch, or the physics term for the pitch is the frequency, will decrease. And we want to talk about why this is. Okay? So a little bit about how sound waves work. We're going to have a whole day about sound waves when you guys come back from this weekend, but just a little tease. If a source of sound is not moving relative to an observer, so you have an observer that's standing in place, a source of sound that's standing in place, the way the sound works is the source creates sound waves, and these waves move outward in concentric circles away from the source. Now what concentric means is it means a set of circles that all have the same center point. Okay? Each circular wavefront has the same center, so we say these waves are concentric. These are examples of concentric waves right down here. All these waves have the same center point. Okay? And when we say that we're talking about all these circles here, these are the wavefronts. Okay? These are, let's say, all the crests of the waves. So all the wavefronts, they are all traveling at the same speed because they're traveling in the same medium. So all traveling at the same speed. All those wavefronts reach the observer on a regular basis, okay? So our observer is standing here, or here, A and B are both observers, and these waves, as they travel outward, they're always traveling the same speed, they're the same distance apart from one another. That means that A and B will hit those wavefronts, those crests, or troughs, or whatever they are, will hit A and B at a regular interval, okay? The frequency of those wavefronts will be the same. And it won't change as long as neither of these sources starts to move. The waves are separated exactly as much as they were when they were created. So as an observer, as those waves are interacting with you, what they do is they go into your ear. The wave fronts, the air pressure differences essentially, go into your ear, and it vibrates a little bone on the inside of your ear. And that little bone is attached to some nerves that go into your brain, and your brain interprets the wiggling of that bone due to the air pressure differences that are sound waves as some sort of pitch. Now, how often or how frequently that bone jiggles tells your brain what pitch it is. And then you interpret that as a frequency, how high the note is. Okay? Your brain is interpreting the frequency, or in other words, again, another name for frequency is the number of waves reaching you per second. Your brain interprets that as pitch. If more waves are reaching you, well, that means that there is a higher pitch. So, that's what's happening here. Something a little bit different happens if either the source of the waves is moving or the observer is moving. And it depends not only on how fast they are moving, and if they're moving at all, also depends on the direction that they're moving relative to the source or the observer. Let me give you a little demonstration of this. Okay, that's enough of that. Here we go. Doppler shift interactive. I can't zoom in on this. That's too bad. So, what I have here is I have a, I don't know, looks like a little planet or something that's emitting light, and I have a spaceship. Okay, I'm going to turn off the lights for just a second so you can get a better view of this. Okay, but I've got a planet or some sort of source of waves. This doesn't have to just be with sound waves. It can be with any type of wave. And a spaceship. Spaceship is our observer. This is our source. And right now I have it checked so that the source will be approaching our spaceship. And the spaceship, what it's going to do is it's going to, there's a graph down here that's going to measure the frequency, or essentially what waves this is picking up, okay? So when it goes across a green, I don't know if you can tell if it's green here. If it goes across a green, that'll be a crest. Yellow is a trough. Crest, trough, crest. The next one will be created will be a trough. So in other words, one, and this is a little misleading, okay? Since this and this are crests, this right here is one wavelength, okay? Not just from green to yellow. So this is a little bit different from the wave fronts as we've been talking about them. But I want you to notice, so basically this has just started to move, okay? I just started the simulation and then I paused it. This has just started to move. So, this will be moving this way. I want you to notice, I'll let it run for a little bit, I want you to notice what is different once it starts moving about the wave fronts, about the distance between like the crest and the trough. So, let's let it move. Oh. Let's do, okay, source approaches. Okay, so this source started over here, moved to here. Now these were waves that were created before it started to move, okay? So far, only waves that have been created before the motion started are showing up on here. We've got a nice, pretty constant wave going right here. But take a look what's happening here. as this source has moved, it hasn't completely caught up to its waves. Okay, they're still ahead of it, but it's not lagging behind as much as it was anymore. We've actually, because this has moved to the left, the waves on the left-hand side of it, they seem kind of like scrunched together. They seem a little bit smaller in wavelength now. On the other hand, take a look over on the right-hand side. Because the source is moving away from these parts of the waves, there's a much bigger distance between successive crests or successive troughs. So watch what happens when this spaceship starts to interact or pick up on those waves. I'm going to unpause it again. This was before, this was afterwards. So we already see that the wave fronts, the distance between the wave fronts have decreased on the left-hand side. What that means is the wavelength seems like it has decreased. Okay? Wavelength seems like it has decreased. Over here, wavelength seems like it has increased. And watch what happens to our graph. Seems like the wavelength is getting bigger, right? And it stops right there. And then because the thing is stopped, it'll move back to normal in a little bit. All right, so let's do it one more time, okay? Before it gets there, I want you to notice, I want to just talk about one last little thing. We said that the wavelength is smaller over here right now because of the motion of the source. It's bigger over here. Well, we know the waves are always traveling at the same speed, and if you remember from the last, or 2 videos ago, we have this equation to regulate how fast, or not how fast, to link the velocity, the wavelength, and the frequency together. If the velocity stays the same, and the wavelength goes down, well, that means the frequency, how many waves reach you per second, must go up. And vice versa. If the wavelength goes up, the frequency must go down. So watch what happens to how many waves the spaceship interacts with per second. We get a much bigger frequency right here. And then as it starts to move past it, we get a lower frequency. This is exactly what happened in the last video with a fire truck. We had a high frequency when this object was coming towards the observer, and a lower frequency when it was moving away. This is known as the Doppler effect. So let's just write down what is actually happening here. All right? We've got